Hello, testing. Okay, good afternoon to everyone. How's your weekend? Huh? How's your weekend? What's this? Why not? Next lesson. Huh? Okay. Okay. Happy doing assignment. Okay. So yeah, your assignment I already finished marking, but I cannot give you back yet. Because we still have some more people need to hand it because they retake. So anyone of you retake? Yeah. So you just joined us, right? This week. Who joined us this week or last week? Okay. Yeah. Okay. So hopefully I can release the assignment when they submit. If not, maybe I will return your assignment first. Okay. If I hand it back to you, please don't circulate or discuss first. Okay, you can read it yourself and then see what's your mistake and then see whether the marking is reasonable or not. Or you think that, hey, this part I should be correct, then you come and ask me. And I think this is the first time you doing proof stuff. So maybe some of your writings, you need to improve. Okay, you need to improve based on my advice. Okay, I will write a comment in your assignment. Okay, so please improve in your. So, Hey, did I talk about fail rate in my class in this year or not? Huh? Are you guys interested? Yes. Interested, huh? Okay. So, do you know how to prevent fail in my class? Okay, good question. So, make sure every time you make the mistake, you improve it. You won't fail in my class then. Okay. Make sure you improve. Okay. If midterm not good, final have to improve. Okay. If you just stay the same very low, then I cannot pass you. Right. Everything you get 30, how I pass you. Right or not? Does it make sense or not? Let me tell you a retake story. There's one person come and retake my AA1. Okay. So can you imagine what happened to him? Huh? But cannot imagine. Anyone want to guess? Retake. Fail again. Sure, for sure, fail. Because that person is the first time seeing me, correct or not? He don't know what's my pattern. Okay? Second time, he came again, wow. Not he, it's not that he is afraid. I'm afraid. He come to take my MA1. MA1. He failed again, not failing my MA1, but he retake, but that time was I'm teaching. Then he know my pattern. He do assignment properly. Okay? He do test properly. I don't say that he do it well, but he do it properly. Write everything he know. Try to know everything. Then borderline, okay, pass. Okay or not? Does it make sense? So your marks are earned by you. Okay, not me. Okay, earned by yourself. Okay, does it make sense? For sure can pass one. Okay, if you put in effort. Okay, if you are 2 week, 2 week, 2 week how? I got one student she study A1, okay, pure max, 2 pure for her. She think that like that. She think it like that. It's normal. So she worked hard for the first pass semester. And then second pass semester, second half of the semester, she gave up. Quarter, what do you think? Fail. Then what happened to this girl? Drop off. You know what she do now? Doing property agent. You think good or bad? Depends. But what I can tell you is her commission is more than my salary. So you need to think properly. If you want to study, study well. If you don't want to study, just go and work. No need to stay here one. Okay or not? If you want to stay here, make sure you study well. Okay? If you don't want to study, just go away. It's fine. Okay? No need to stay here. You susah, I also susah. You know what I mean? Chinese guy, you know what I mean? Hey, how you know? How do you know? English? No, I'm speaking Malay. I susah, you also susah. Susah is what? Huh? Oh yeah, Roger. I mean, okay then. I mean, do you know what susah mean? Huh? Kill yourself. Almost killing. Okay, killing is okay. Suicide. No, suicide. You think it's suicide. Oh, okay, okay. Suicide. SUSIH. So you feel hard, I also feel hard. Okay, so we don't need to feel hard to each other. Okay, so if you decide, retake, or stay in this class, make sure you study well. Okay, if you think this part hard, difficult, come to my office or that's all. Okay, you just learn whatever you can. Okay, if I see you can improve, then for sure you can pass on. Okay, if you improve still under 50, then you need to think about, are you really want to stay in this degree or not? This is about ability problem already. Understand or not? Okay, but let me tell you it can work out one. Okay, it can work out. Because the first year when I studied analysis, I also failed. But luckily, that course is like linear algebra plus calculus. So my linear algebra very good. Okay or not? So if you want to do it, you can. Okay. If you don't want, then no, don't do. Okay. If you can, you will do it. Okay. If you want, you can do it. That's what I mean. Okay. If you don't want, no need to do anything. Does it make sense or not? Okay. So make sure if you want to stay in my class, 下定决心读书. That's all. Okay. You can play, you can relax, but don't forget to study. Okay. Okay, so maybe I talk a bit about your assignment. So some of you you stop using approximation. It's not that it's not allowed in mathematics, but it's not allowed in this course. Okay, you need to know that our course is calculus. Okay, or analysis. What we do in calculus or analysis is about bound. Okay, there's no calculator or computer in the old age. How they use approximation? Cannot. Okay, we use bound. Okay, so we learn how to bound. So you will see that we learn squeeze theorem or what, something like that. Right, squeeze theorem, increasing, decreasing, or using the inequality. We want to look at bounds. Okay, you need to use bounds. Okay, approximation is not happening in this course. We got ME doing those things, numerical method or optimization. Okay, these are about approximation. Okay, we don't do approximation in this class. Okay, some of your assignments you try to use approximation. No, even for limit, we also use bound. Remember or not? Epsilon delta. Use bound by epsilon, bound by delta, bound by n. All of these are bounds. Okay. Yeah, it's bound. We use bound. Just using bound, you can do maths. We will talk more when we discuss the assignment later, but these are very important things. Also, this kind of presentation I don't like. Don't use 3 dot, triangle dot, or inverted triangle dot. Don't use this. Ban in this course. This class. Okay? So if you want to use a triangle one, what word you should use? Hence, so, therefore, it follows that like this. If you want to use inverted, you can use since, if, as, because. Okay. If you want to use maybe at most this one, hence, only use once. Don't use like this in sequence, I don't want. Okay, can you recognize or not? Which one is hence, which one is if? Can you recognize? Very messy. Okay, don't use these. I have this kind of story. This happened even when I was studying in ANU. I was a tutor there. I also mark assignment. I mark assignment. Typically, Chinese students will use this. Then I asked them why. 为什么你们喜欢用三个点放来放去 He said that to save time, because in their Gaokao, they don't have enough time. Is it true or not? Let me ask the Chinese student here. Yes, right. Okay, so that one is already high school, passed already. Okay, now is university. Okay, we use that. Use word. Okay or not? Okay. We should have enough time for you to write down this word. Don't worry. Okay. Let's try and learn, use these word. Don't use this kind of presentation anymore. Okay. So any question from last lecture or not? Did you start trying to do the tutorial question already? We have enough material content to start the tutorial questions. Please do. If you just relies on assignments question, you won't learn much. Okay, you need to do the tutorial. Okay, do to the extent that you think, oh, I know this concept already. Okay, if don't know, try again. There are 2 books for you to do, or I put inside. One is Stewart, one is Adam. Okay. Sometimes for conceptual question, I will take from Adams. So you can try those also. For both of them, I have put out the solution manual. So Yiping asked me about this solution for chapter 11 Stewart. Okay, the previous one, I think it mixed up that chapter. So I think I'm out of the other one. But that one only have odd question solution. Okay, so for the even one, you can try it out. Okay, or if you are not sure, then you bring to office hour to check. Okay, yeah, try and practice them. Okay, so before we continue with series, let's do some um, sequence question quiz for you. So the question is this. So can we remove the middle term sequence without altering convergence? So last time we talked about that if we remove first few term from the sequence, the convergence of the sequence won't change. Okay, if it diverge, if you add the first few term back, it still diverge. If you converge, if you add the first few term back, it still converge. So what if I remove the middle term? Does it affect the convergence of sequence or not? To your friend also. Middle meaning including you can take anything in between. Okay. I don't restrict how many you can take. Sure, you can. Any idea? Yes or no? Every time you come into my class, you have to make decision. You need to learn to make decision in your life. True or false? If wrong, never mind. You just need to be responsible, but don't push your responsibility away. Okay. So yes or no? You think yes? How? What do you mean? Can you give me an example or not? Because if you say yes, then you need to give me an example, right? Give me an example, right? Either you prove it or either you give me an example.
Example to prove that works, right? Just
I mean, this is how to say.
if I have a counter example,
Yeah.
that's not true, but if I have an example, that's not a proof.
Wait, I mean, wait. What question are you answering now? If yes, just say that it is possible, right? I'm not saying that always possible. You get what I mean? So it's a bit different here. Right? I just asked you, is it possible? I didn't say that it is always possible. Okay.
Zero.
Hmm?
I can consider
N equals 0, then
sum of parents is always zero, or whatever you take. Because
it's still conversion. But I said whether it, let me see. Can we remove without? Oh, okay. Yeah, sure. Okay. Yeah, sure. Okay. I mean, no need to look at the series, right? You just look at the sequence. Okay, just look at the sequence. So this sequence will converge to 0. No matter what thing you take away, it still converge to uh, 0. Um, cool. What if is it always true if we take away infinitely many terms? Is it always true? Is it always true if we take away infinitely many? If we can take away infinitely many? Next question. Is it still true if we can take away infinitely many terms from the sequence? Is it still true? Always. Is it still true? Always. Still true? Just try. Wrong also never mind. If yes, like what he said, you need to prove now. Now it's always true already. Mm, 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 mm. Oh, okay. So you didn't take that. Maybe a valid way of thinking. Can you prove that? Oh, the last one, huh? Mm. But the convergence here also include divergence, oh, by the way. This convergence here also include by the divergence. When I say convergence mean whether it converge or not. Whether it converge or not. Okay. Maybe this sequence converge, maybe this sequence diverge. Okay. Yeah. Why? Okay.
You take away the whole infinitely many terms in between, then left the one and then the last one. You got one and one, so it converts to one. But however, it originally diverged.
Okay, maybe we can give a simpler example, right? Can give a simpler example. So let's say we got this diverging sequence here. What's the simplest diverging sequence that I show you? The alternating sequence minus one and one. So this guy diverge, but if you remove, let's say, all the one, then this sequence will converge. Does it make sense? Any question? 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 Any question? Yeah. Yeah. So can you remove infinitely many terms of your sequence, okay, such that the convergence changes? Okay. Does it make sense? Okay. So if you consider sequence minus one to the n, okay. So the one in an, we get uh, we get n close to one, then for all -1 for all and on converges to consider this language. Okay. Okay. Does it make sense? Does it make sense? Okay. Okay. Question? Term of sequence line in number line. What do you mean? From the same. Real line, then
I don't know. So,
and then uh, yeah. Sure. Then I'm not sure. You try and write it out properly. Try and write out and send to me. Yeah. Try and write out and send to me. Okay. Somehow think like you are talking about some quite advanced thing here. Okay. How about the others? Is other okay? Are you following? I'm trying to say. Okay or not? So you need to be careful when you remove term from your sequence. Okay, how you remove these terms. Okay, you need to be careful. Okay, you cannot simply remove terms. All right. So let's return to what we left last time. So we left from the integral test. Okay, we didn't prove it. So what's the integral test content here? Suppose what? Suppose f is a continuous. Sorry. What other condition you need? F have to be continuous. Positive, good. And decreasing, good. Okay. Once you have these, what property you have? The integral of f, x, yes. So this function is going from where? So whenever we talk about function, you need to be very sensitive. What's domain? What's the codomain? Okay, you need to be sensitive here. So what's this domain codomain here? Should be just R to R. Okay. So you can integrate this function from, in particular, from 1 to infinity. So this integral converges if and only if the sum of this f, okay, applied to the positive integer also converges. Okay, is it clear? So this f here is restricting to the natural number. Okay, restricting to the natural number. Have we fixed our natural number yet? We fixed already, right? Starting from 1. Okay. Yeah. Everyone follow this notation or not? So if you have a function, you can look at what is f1, f2, f3, f4, f5, f6, f7, f8. So these form a sequence, right? Last time we talked about sequence can be defined by function an equals to fn. Okay, look at these natural number point here. Okay, so we're gonna try and use this to prove some convergence. Okay, so how should we do this? So should we demonstrate once? Okay, let me demonstrate once. So let's say check this conversion here. So we want to check the convergence of the series n equals to 1. Check the convergence of this sequence, this series here. Okay, so we're gonna try and use the integral test here. So what's the sign to use integral test? You need to follow the three conditions. Okay, you need to check the three conditions. But first, it should be a nice function that you can build up from here. Okay, so what can be the function you try and look at? What can be the function you look at here? Let fx be what? And how do you turn your sequence into a function? You just, instead of evaluate at n, you evaluate at x. Okay, so you get fx equal to 1 over x squared plus 1. Okay, correct or not? If you have this function, restrict to the natural number point. Is it the same sequence you get? Right? If you put n here, you get the series. Okay, so three things you need to check. So one is continuity, continuous. Second, positive. Third, decreasing. Okay, so three things you need to check. So how to check continuity here? So there's no epsilon delta for you to play around in this class. So you need to argue by general argument here. So the general argument here is composition of continuous function is continuous. Okay, did you guys know this from calculus 1 or not? Composition of continuous function is continuous. Okay, so you need to remember this fact. Composition of continuous function is continuous. So can you see that this f is a composition of continuous function here? So you should know that x is continuous. Okay, the identity function is continuous. And then x squared is also continuous. Okay, product of continuous function is also continuous. And then you can do shifting by 1. Okay, and then you compose with 1 over x. Okay, 1 over x is also continuous. But be careful, 1 over x only continuous away from 0. Okay, so the region that we care here is where? Do you know what region we care here? From where to where? Yes, that is the place that we do integral later. Okay, so we're only interested in this region only. So 1 over x is continuous in this region. Okay. Okay, so for this one, I will argue that since x squared plus 1 is not equal to 0, in 1 to infinity, and so f is continuous. Okay, f is continuous. Continuous being a composite of continuous function. Okay, so do you guys know some basic continuous function or not? For example, polynomials are continuous. Trigonometry function are continuous. What else are continuous? Trigonometry, polynomial. Exponent, good. Exponent are continuous. Anything you guys learn is continuous. These are continuous everywhere, everywhere in R. Okay. 1 over x is continuous away from 0. Ln x is only continuous on the positives, real number. Okay. Yeah, so these basic things you can use, no need to prove. We will only these will be only proved in MA1. Okay. Right. How about positivity? Is it positive or not? Is it positive or not? So where we consider these x, x is only considered from 1 to infinity again. Okay, so you ask yourself, is it x squared positive or not? Okay, x squared is positive. Square should be greater than equal to 0. So positive, right? So it should be greater than 0. This will imply that x squared plus 1 is also greater than 0 because it's greater than 1, so greater than 0. Then you are inverting something greater than 0. So it is still greater than 0. Okay. Decreasing, how to show decreasing? How to show decreasing for a function? What way can we use for decreasing or increasing function? Okay, I think in you guys learn or not? Calculus one. What do you do? What do you check? Derivative. Okay, good. So you check your first derivative. To be decreasing, what's the first derivative have to be? Huh? What? I heard something. Decreasing means what? The first derivative has to be what? Less than 0. Okay, so we need to check this. Whether the first derivative is less than 0 or not. So if you differentiate, what do you get? Minus 2x over x squared plus 1 squared. Okay. So you better hope that this number here is less than 0. Okay. So if you look at this denominator here, what can you infer here? It's always positive, right? No matter what you put inside this box here, because it's x squared. Okay, so it's positive. How about here? Depend on x. But where is my x? 1 to infinity also positive. So this portion here is always positive. Okay, but we always have a negative. Okay. So this is less than 0. Okay, for x in 1 to infinity. So now we can use integral test now. So if you compute that this integral here diverges, then your series also diverge. If converge, then it converge also. Okay, so can you all try and compute this? And then we can check answer again. Try and compute this integral here. And compute. Okay, so to do this improper integral, right, you need to turn into a limit of a definite integral first. Okay, and then you try and integrate. I think to integrate this, you need a trick, right? You can straight away get the integrand to be e. Okay. Then what is this equal to? Sorry. So this is equal to tangent inverse t minus pi over 4, right? Okay. And then this is what? Pi over 2 minus pi over 4, which is pi over 4. So it converges. Okay, so this implies that the um, series also converges. That it just implies convergence. I didn't say this sum have to equal this integral. Does it make sense? I didn't say that. We don't know what this sum here is. We don't know the limit of this um, series. I mean, the sum of the series. Okay. Correct or not? Still remember the diagram we draw last time? If it converges, this area here should be something less than this integral. Something less. Okay. Less than or equal to at least. Okay. So I only can claim convergence. I don't know what's the sum. Okay. But later, if we do Fourier series, some other technique will help you to find this kind of sum. Okay. Let me see. Yeah, anything to add here? Okay, so in my course, no need to worry of this kind of integration here. If I gonna use this kind of integration, I will supply you the formula. Okay. The, the main thing I want to train you is not about this formula, but I want to train you how to think mathematically. Are you guys okay or not with this integration test exercise? Can we skip examples? I let you try yourself at home. Yeah, it's really the same way. Uh, yeah, I'm not trying to lie to you. Yeah, it's the same way. Okay. Yeah. So basically, the hardest part I think is this decreasing because we don't really emphasize on continuity already. So it's a decreasing part and the integral part. Okay, if it's a normal integral, it should be okay. But if it's like a trigger thing, then I will supply you the formula. Then nothing to worry about. Okay. Yeah. Um. Cool. So I will leave the other exercise for you to do. So let's continue. Go to the next test. So far, how many things we have gone through? So we have gone through what? First thing we've gone through in the series is what? Geometric series. Okay, geometric series. Telling you that when the series such as a to the Rn converge, right? So let's not write this down. And then what else we see? What else we see after geometry series? Is it test for divergence? Maybe someone can help and check. And then integral test. Okay, so far we have learned this three. Anything else? Anything else? No? Okay. Okay, good. So far we learned this three. So the next one we're gonna learn is called a P series. Okay. So what is P series here? The theorem is the P series as defined on the spot. What is P series? The P series that is sigma of n to infinity of 1 over np is convergent if and only if p greater than 1. So you have seen this kind of series already, right? In particular, we have seen when p equals to 1. What is when p equals to 1? Harmonic series. What happened to harmonic series? diverge. But more importantly, it not just only diverge, it is a counter example to some statement, right? To the test for divergence. Although the every terms, if you look at 1/2, 1/3, 1/4, the limit of this AN converge to 0. But when you add them up, it doesn't converge. It add to some infinity. Okay, it diverge. Okay, although you are already adding pretty small number together already, but still, okay, the effect is large. Okay or not? So what else we seen? We also seen when p equals to 2, right? P equals to 2. We use the integral test to prove that it is convergent. Correct or not? 1 over x, 1 over n squared. That's the example for our integral test. What else we see? 1 over n to the power half square root n. That guy diverge. Okay, so far make sure what says here. Only when p greater than 1 it converge. Okay, so we need to prove. Okay, we need to prove this. So here the statement is if and only if. Okay, if and only if, meaning there are two directions. Okay, two directions you need to do. Okay, two directions you need to do. So I'll put the proof here. So let's prove the backward direction. Okay, backward direction. Suppose that p greater than 1. So what's the strategy here? What's the strategy here? So there's a very good reason, right, why we do things in order. So this theorem was due after integral test. So you want to show some series is convergent. Maybe we need integral test. Okay, so we can try and use integral test to show what? What's our goal? We want to show that the P series is convergent. Okay, so if we want to use integral test means what? We need to produce a function first. Okay, so what kind of function we need to produce? So the strategy, let me put down the strategy first. I'm not sure it works or not. Let's put down strategy. Strategy, use integral test to show this P series here converge. Okay, so if we're going to use integral test, what do we need to check? We need to produce a function first. So what function we should look at to study this series here? Fx equals to what? X equals to what? Remember, what does this function do? When we restrict x to n, we get the an term. So meaning what? You just replace the n by x. Okay, so we should consider the function fx equal to x to the p. Because when we evaluate at the n, we will get back our term inside my series. Okay. So what do we need to check? How many things we need to check here? How many things? 3 things. Okay. So what's the first thing? Continuity, and then positive, and then decreasing. So you need to check these 3 things here. Okay, is it continuous or not? It's not continuous everywhere, but it is continuous at where we care. Where we care? Where do we care? 1 to infinity. So from 1 to infinity, this function is pretty continuous. Okay. Positive? Is it always positive or not? No, huh? But where do we care? Where do we care? We only care for x from 1 to infinity. The thing that we input is always positive. Okay, so no matter what power you take, it's still positive. Okay. Decreasing it. So same technique just now, right? We can look at the first derivative. What's the first derivative here? Minus p over x to the p plus 1. Okay. So p here is positive. Okay, numerator positive. Denominator is also positive, like what we argued just now. Okay, so minus a positive thing, you always get negative. Okay, does that make sense? So this is always negative on 1 to infinity. Any question? Okay, so we already satisfied the integral test property already. So what's the next thing we hope for if we want to show this series converge? What's the next thing we hope? The integral have to converge. Okay, so the integral have to converge. So we still do integral from 1 to infinity. So the improper integral. So what's this integral here? So I'll quickly compute it. So you can check or you compute. So the answer I think is 1 over p minus 1. Okay, okay. Check. If you get the same calculation. Okay. Okay. If this is true, then this is finite. Okay, so meaning converge. Okay, so by the integral test, the P series also converges. Okay. Okay. Okay, so what about next one? How about the other direction? So what's the other direction here? If this series converges, then P has to be greater than 1. Okay, so this is the other direction we need to prove. But instead of proving that direction, I mean using a direct proof, we will prove by contrapositive. So what's contrapositive here? If it is not greater than 1, meaning what? If it is less than, if P is less than or equal to 1, then we want to show that P series diverges. Okay, we want to show that P series diverges. So many P, right? So how are we gonna do proof for all P? Okay. So if you try and test different P, you can split P into 4 cases. Okay. So we consider 4 cases for P. Into 4 region. So first is P equals to 1. Second is in between 0 and 1. And then P equals to 0. And then P less than 1. Less than 0. So in this 4 region, right, you can see that they diverge for different reasons. Okay. So P equals to 1, you know already, right? For P equals to 1. Okay, for P equal to 1, what we get is really just harmonic series. Okay, we prove that it diverges. Yeah. Okay, so when P equals to 1, it diverges as a harmonic series. How about P equals 0? Maybe let's do P equals 0 first. So what is P equals 0? I think this one even simpler. This is just sum of 1. Good. So this diverges. Why diverge? Why diverge? Why diverge? Why diverge? diverge. I Seng Y diverge. Oh yeah, right. So you can use test for divergence, right? Because limit of an is what? 1. 1 is not 0. Okay, so diverge. Or you can use divergence test. Because lim of an, which is 1 in this case, is 1, not 0. Okay, so how about the other cases? The other cases, though, maybe look at less than 1, less than 0 first. Okay, what if this series is less than 0, with power less than 0? For these, you also can use divergent test. Can you see it? Can you see it or not? If p is less than 0, what happened to this series? What's this sum here? You need to imagine a number, for example, right? -2. If I put a -2 here, what happened? 1 over n minus to the power -2. Yeah, become n squared. Okay, become larger, right? So actually you are doing n to the, let's say, modulus power of p. Okay, larger. So an become larger. So we can think about divergent test again, right? So if we consider limit, the limit of 1 over np, which is just limit n to infinity of n to the power p, and then this limit is actually infinity. Okay, infinity, and then it is greater not equal to 0. So again, by divergent test, the series diverges. Okay, so we left with one more cases in between 1 and 0. So in this case here, there are really only 2 tests we have learned, right? So you can try, you want to try divergence, maybe you can try, but we're going to use integral test here. Okay, so if we use integral test, we will get the same calculation. So let's not calculate again. So let's copy this. Let's see. Copy. Yeah, copy this. Let's copy down here. So let's look at this integral again. Can you see anything new or not? If p is in between 0 and 1. We squeeze, we move a bit. So if p is in between 0 and 1, can you see anything new for this limit? What happened? If p is in between 0 and 1, this p is less than 1. You take something less than 1 and then take the difference, what do you get? What do you get? What do you get? If you take something less than 1 and then minus 1, you take negative, right? Okay, so a similar story here, right? 1 over t to the negative power. So it becomes a positive power on t. Okay, so this is growing. This term is growing. How about this term? This term is just a constant. Okay, so you have a growing term here. Okay, so this term will grow to also infinity. So you can use that by integral test, the actual series, languages. Okay, or not? Okay, yeah. Okay, good. Okay, I think we stop at the correct time. So if you look at the actual notes here, there's a part for remainder estimate here. Okay, we won't touch it. Okay, you can learn it by yourself. You can do it if you want. Okay, but we won't test it. Okay. Yeah. So because the my focus for this course is a bit different. So there are some application for this kind of theory, like for this remainder estimate, this kind of thing, I will skip. Okay, but you can learn. Maybe for future it's useful, but for tests it's not. Okay. Because the philosophy that for me to teach is I teach you the basic. I teach you the basic, you know enough that if I go ask you to read this, you can read it yourself, actually. So I don't need to teach you everything. Okay, I teach you the main thing. And then you can use this main thing to apply to different cases. So I won't teach you everything in this one. Okay. But I will catch the basic a lot. Okay, the foundation. I'll play around with the foundation. Okay. This kind of calculation, I think if you look at it, you also can do it. Okay, so we won't worry this much. Okay, any question before we take a break? Okay, if no question, right, we have finished integral tests. Later we'll come back for comparison tests. There's a lot of tests we need to go through for this series. Once we finish these tests, we will leave this chapter. Okay, so let's break until 209. Yu, 金童, yep. 小鹏, check you, I saw you right. It's not about check you right. Okay. 林, 丁雄, 恩琪, Yu Huo, Chen, Wu Ping, Ping, Ping Liang, 魏琪，魏琪，哦，为什么我想不起他脸？要再看一次。凯伦，OK，一翔，OK，全，安波，小莹，小杨，小杨有没有 submitted your assignment？有 submitted OK，you join us earlier 哈。一平有没有 submitted your assignment？OK，洪杰，OK，洪杰 and 昌云，you come here for what？Later you two have to contact that. Jinsen, we got newcomer. Need to add them in. These two person. That two. Yeah, can you guys come here for one? I want to talk to you guys. Yeah, 看过，对，这种，对。 来得及吗？
在第一天会就怎么说明那个美元可以
哦，OK，OK，就 suppose，你可以 suppose，但是你到最后要证明说，它每一个 term 是它符合那个 Fibonacci 的 definition。你是说你不知道为什么可以从？你是说你不知道为什么可以从这个开始吗？
对，
呃，我觉得你可以 suppose，你可以就从这里开始，然后你最后要 argue 的东西是说你的AE 要等于一，你要 prove that 你的 AE 等于A2等于一，然后还有 AN 等于 AN 减一加 AN 减二，这是你要证的两次就可以了。
进行
如果你要的话，就比较 specific 一点，就是说新的那个东西把它叫成 BN，就是说，然后 B1要等于一，B2要等于这个，然后 B 就所有的 n 大于2的 Bn 都要等于 Bn 减一加
明白了。
呀。所以你们上学期的成绩，我要知道一下。
我其中挺好吗？
哦，其中一个是 OK，你呢？
不太好，对，
不是你就是比如说整个学期下来，你学了什么东西，还是都没有？
对，像是
这样
斯
比较
度的话，也是像不期中减，
其中之后的
对，
OK OK，因为你们现在因为你们迟进，所以你们 miss 了2个星期的课。如果能的话，听回我的 recording，OK，可能不用每一个字都听了，但是你一定要去抓一些我要看重的东西不然的话，你会再次感到迷茫在这个课里面。嗯，但是就是说，如果真的来说，这个拜五前你是交不了，你也要告诉我。然后就是你必须要制定一个比较合理的，就是读书的方法给你自己。因为我不知道，可能有些人要长一点时间，有些人要短一点时间，我不知道。你就要制定一个你可以执行的一个计划给我，然后我看一下合理吗？可以跟我搭配，你明白吗？OK 吗？你 for assignment 这东西不是你全部可以找资料的，你可以上网找资料，但是只有一件事情吧，你不可以抄，就是说你要理解过后用你的理解把它写下来，写好不好是另外一回事，但是你就要用你的自己的理解。OK，如果你找，比如说你找资料说我还不懂，那你就拿来问我，你可以拿来问我。OK，如果你有跟同学讨论什么你也可以你就要写下你跟谁讨论，OK 吗？可以吗？可以吗？可以。OK，有问题吗？你没有问题吗？不要说好像什么很怕我这样还是什么这样，因为你有什么问题你一定要提出来，因为如果我不懂的话，我不能够帮你解决，就或者我不能够跟你一起想办法，你只能够自己吞吧。OK，你试一下能不能星期五做完。如果你这几天看了觉得不能，看下有没有比较合理的方法。因为你要记住一个事情，就是我要跟他们讨论答案，所以是说我要在下一个之前跟他们讨论。这样的话大家才知道要怎么改进，下一个他们就不要再做这种事情了，明白？呀，嗯，这样子有问题吗？
没有，
暂时没有。招募的怎么办呢
知道，
？OK，好。等一下我要单独跟你说一下，如果你没有问题，你可以直接说。你找他把你加进那个，我们有一个群组，就是听的群，就是他们学生自己，就是说有什么问题可以问他们，大家可以在里面发问。不管是作业还是这堂课的补课，还是什么各种各样，关系到学校都可以在那里大家问这样。
对，
那一位那个红衣呢，那个褐色衣服那个，
最后一
最后一呀，你可以找他讲一下。OK。
你是长你是蹲在他里面，你是来回摸你啊？你回了你的白色，回了，因为他在着急的找你，因为他说你有一个 visa 的问题，你有 visa 问题。
没有没有，我签证是3年。
OK，但是他们上面是说，因为你的成绩对你要签的是什么？
哦哦
也因为对，因为你的成绩全部达标了，然后你的 visa 会找，
哦
你要回复他，他
哦
在着急。
我回过了，他们说昨天下午3点
OK，
跟我
然后
聊这个事情，然后我昨天下午3点上线，然后他也没找我，应该是没什么问题啊，因为正常来说签证是3个月，然后我是运气好一点，签证有3年，然后就没有这种
我不知道，因为他是那个 management，就是说 AA 那里告诉他们，对，他就找你了。
哦
但是
我再回去查一下，
你再回去查一下，Pauline 有找你，
嗯
奇怪，因为是 AA 告诉你，所以但是你就可能要照顾一下你的成绩哦，多少啊不可以要超过2.0，
哦，
2.0以上，
要我超过
2.0所以嗯嗯，好，你第几年来着？第2年第一学期。
哦对，
所以你现在拿了还有什么课？
哦你说你说修
对对对，
还有这个概率论，还有你的那个抽象代数，
OK，嗯，我觉得啦，可能你同时拿2门课会蛮压力的，所以就有什么问题你一定要来那个 office 啊，如果跟不上的话会很辛苦。
谢谢。
可以啊，这样你找他，这样把你加进那个群组里面，等下有什么消息他们会在那边通知，我没有搞，有没有？哦，OK OK。Okay, so let's continue. Let's continue with a direct comparison test. Or sometimes we will call it a simple comparison test. Sometimes you feel weird why I want to tell you two names. Because the main reference that we give you is using direct comparison test. But usually when we go higher level, we just call this a simple comparison test. Okay? Or different textbook will use simple comparison test. So they are referred to the same thing. So what does the simple comparison test do? So 顾名思义嘛 you need to compare something. Okay, but how do you compare? This is very important. So what do you compare is you need to compare positive term. Okay, so they are positive sequence such that Bn is greater or equal to An and then greater or equals to 0 for all n greater or equal to some n. Okay, some n is enough already. Okay, after a capital N is enough. Okay. So what's the segment here? So the segment here is if the sum of Bn is convergent, then the sum of An is convergent. Okay. Second, if sum of an is divergent, then sum of bn is also divergent. Do you think this idea is familiar or not? Is it familiar? Familiar or not? Why, King Xiong? Why is it familiar? Why? Convergent test? What test? There are only two tests we know, right? You picked the wrong one. Okay, it's okay, it's okay. Yeah. What? Controversy? Yeah. Okay, I mean, sure. The second statement is the contra positive for the first one. But if you think about this sentence, right, we have already seen this idea before. You bound an by bn, and then both of them are positive. Correct or not? The integral test, right? The function is positive, decreasing continuous, right? So if you can think of this bn as the function, right? If the function is convergent, then the an also converge. But this case here, the bn we consider here is not function anymore. It's also single points, okay, sequence. Okay, does it make sense? Do you know what's the picture I'm imagining now? No? So let me draw it for you. So let me draw this picture for you. So you can think of an something like this, right? And then bn is on top of it. Okay. So instead of considering a sequence bounded above by a function, you think of it as bn also. Okay. So you can see that if this bn, if they sum together already converge, surely the smaller, the lower one also sum to some finite sum. Okay. If the lower one diverge, okay, if the lower one diverge, surely the larger one also diverge. Okay, so this is some how to say, this is some ideas you should think about when you consider this segment here. Okay, does it make sense? Make sense or not? Does it make sense? Okay. So how are we gonna prove this? How are we gonna prove this? So let me show you one proof here. So let me show you one proof here. So let's do one proof here. So let's prove the first segment since I say that the second segment is just contrapositive. So it's just enough to prove one of the statement. So let's suppose the series of Bn is convergent. And then we want to show that sum of An is convergent. So how are we going to prove it? So there's bound here, right? So we somewhat need to use the bound. Okay. Let's see how we use it. So let's consider the following n partial sum. So there are few partial sum we can look at. So let's look at Sn, where it is the partial sum for Ai, and the partial sum for Vn. So we look at this partial sum. So by assumption, what do we know about these partial sum? By assumption, what do we know? By assumption, what do we know about these partial sum? Sure. Okay. Sn is squeezed by 0 and Tn. What else? Do we know anything about Tn or not? Tn converge because the series of Bn converge. Okay, so Tn converge to some number. Let's say T. Okay, that is T.
Okay, so T equals to the sum for the series. Okay, and note that what you are adding are all positive number, correct? Okay, so this implies what? These sums are, in particular, non-decreasing. Okay, non-decreasing. Not strictly greater than zero, maybe sometime equals zero. Okay, so that's why we put non-decreasing here. What else? Can we put things together now? So what do we? So also note that we know that AI less than equal to BN. Okay, so this implies that Sn is less than equal to Tn, right? Okay, this is what we had just now. And what? So Tn is always increasing. So we should know that this Tn is actually less than or equal to T. Yes, this is the only way you can get the limit. Actually, this part a bit dodgy. Next time I'll tell you some part is dodgy. Then you don't need to care about. So to be precise, you need to show this why this limit has to be greater or equal to Tn. But can you try and how to say imagine why? Because your Tn is increasing, not decreasing. Okay. So the only way you can go to the limit is approaching from below. Does it make? But to show it precisely, we need epsilon delta actually. Okay, but can you get the idea? If your sequence is increasing, keep going up, but you need to meet a limit. How to meet a limit? You need to go from below. Otherwise, you will go nowhere because your sequence keep increasing. Okay, so hence what? Hence, so which part is dodgy? This part. Oh, yeah, to be precise. So hence, Sn is monotonic and bounded. Okay, so by the MCT theorem, the series is convergent. Okay, so for this kind of proof, when we say we need epsilon delta thing, right, you can do it in your project. Okay, let's say you can prove this statement in your project. Okay, by filling this reverse gap here. Okay, in future, I'll try to skip this kind of proof. Okay, we don't waste time discuss this kind of proof because it's not precise. Okay, sorry that I present a not precise proof to you. Okay, any question? Any question? So even though it's not precise, but I show you an instant how we use MCT. Okay, MCT is really useful. It's not just for calculate whether sequence conversion. We can prove other statement using that theorem. Okay. All right. So this is comparison test, right? So can you imagine how to use this statement here? So first you need to get to this inequality first. Okay. Then you need to at least know one of the convergence of your series. Only you can deduce for the other. Okay. So what type of series you know when to converge, when to diverge? There are two types of family of series you know, right? The geometric series, the P series. Also, there's one specific series you know, right? Harmonic series. Okay, you can compare to this series first. Okay, so let's do some exercise. So let's do two exercise now. Okay, I give you 3 minutes to do it. So first exercise is the sum of 5
over 2n squared plus 4n plus 3. And then the other one is sum from ln n over n, all from 1 to infinity. Okay, yeah, try and check whether this converge or diverge. You can discuss that with the friend in front you, behind you, beside you. And please make friends in this class because life is really hard. Because I make your life hard. In front you, in front you. Make some friend in this class. Maybe you still want to use integral test, but try and think about direct comparison test first. Okay, simple comparison test. You go home, you can try whether you can use integral test or not. So in mathematics, right, a very important skill is can you relate something new to what you have learned before? Okay, can you relate something new to what you have learned before? Okay, in this example here, I'll show you how to relate to what we have learned before. Okay, so these two examples comes after simple comparison test. So meaning we need to compare to some series that we have known before. So let's look at the first cases. So what's the AN sequence we're looking for here? Is 5 over 2n squared plus 4n plus 3. Okay. Obviously, this guy is greater than or equal to 0. Okay, but what can bound this sequence? What can bound this sequence? Sorry, say it. What do you mean 3 to 2? Change it to 3 to 2? What do you mean?
You mean 2n squared plus 4n plus 2, like this. And then how do you factorize? You mean you want to factorize as 2n plus 1? Okay. So you mean you mean factorize. Okay, factorize this. So you get n squared plus 2n plus 1. And then equals to the 2 times n plus 1 squared. Okay. And then this guy converge. How do you know? You mean what? Okay, so you are claiming that this sum here converge? Is it? Why? How do you prove it? P 大于 E. But okay, wait. Seems like it. Can everyone see this as a P series or not? Huh? Yeah. Wait, let me write it properly first. So n equals to 1 to infinity. So Xiaopen said this is a P series in disguise. Can you see it or not? Can you see it or not? This is a P series in disguise. So maybe we rewrite this a bit. 5 over 2 of sum of n equals to 1 to infinity of 1 over n plus 1 squared. Alright? And then n plus 1 is just shifting by 1, right? So we can regard this as a P series starting from 2. Good idea. Okay, so we know that the P series converges. So by the property of convergent series, the scalar multiplied to the convergent series still converge. Okay, make sense? Okay, but this is not my answer, but this one also work. Okay, this also work. Okay, this also work. So I can get to this series faster. So what can I do? I simply throw away the lower power term. I just throw away n 4n plus 3 instead of just throw away 1. Correct or not? If I make the denominator smaller, that means I can make the quotient larger. I simply throw away all the lower degree term. Okay? Because all these lower degree term I throw is also positive, but you need to make sure. If you throw away some negative one, then you will be in trouble. Okay, because we take away a positive number. So similarly, sum of this 5 over 2 to the n squared also converge. Okay, similar argument. You start at 2, I can start at 1. Okay. Yeah, so this is the reason why I don't want to teach you one method. Because I don't want you, I want you to have your own idea. I want you to develop your own way. Okay? Because in research, we don't like to see the same solution. We want to see different solutions. Only different solution can work different path. Okay, no? Even maybe we all get the same answer, but different way of solution is what make research vibrant. Okay, no? So that's why you rarely see me teaching. You must use this, must use this, must use this. No, but even in assignment, you can use different way. But the where have to be inside our course. You cannot say, oh, I want to use approximation. I never taught in this course. Why you use it? Correct or not? So there's also still a bound there, but this bound is pretty far. So please don't go outside this bound. Okay or not? Don't go outside this bound. This bound is already quite big. Okay, don't find a back road. Okay, yeah. So use the tool I gave you. Just that how to use this tool can based on your creativity. Okay, based on your creativity. See, for this example, right, I teach you P series. I teach you simple comparison test. Go and play. See, Xiaopeng already play a different way from my way. It's good, which is good. This is what I want to see in your assignment actually. When I see different solution which work out, I am very happy one. Okay, next question. So next question. So how about long n over n? Can you bound something or not? Bound by something, or we get bound by something else? Long n over n. Okay, do. Sorry. Restrict to n larger and equal to 3 and then so for every n greater than equal to 3, what happened? Long n greater than 1. Can you prove this? N 大于 e, oh e, long e. Okay, this is sorry, e as e. English 1 okay. So long n greater than 1. So this is if only if n greater than e like that. Okay. So you know that e is less than 3. No calculator. If there's no calculator, do you know it? Can you prove it or not? Okay. So this, I think this need to rely on some other facts. Anything you learned before? So let me think. Yeah. Yeah. So we need to use this fact, right? Okay. So if we know this fact, what do we need? What we can play with this fact? Yeah? If we know this fact, what can we do with this fact here? Does all of you know why this n greater than e or not? Why? Somewhat you need to know about the exact value of e or not. E is like 2.7 something. Okay. Let's assume this something. Okay, so if you know this, then what to do? So this implies what? Log n over n greater than 1 over n, okay, which is also greater than equal to 0. But we know the sum of 1 over n, right? What happened to the sum of 1 over n? We know that sum of 1 over n averages because this is a harmonic series. So we can use simple comparison test. Okay, because the smaller sequence have a divergent series, we know that the larger sequence will also have a divergent series. Okay. Okay. Yeah. Yeah. So for this kind of thing, you also not need worry one. No need worry of this kind to memorize when is this greater than this for large n one. Because if we're not gonna prove this, we're not gonna use this unless if I want to come up question like this, I will tell you in the hint 3 is greater than E, something like that. Okay, I will tell you. Okay. In my exam, I try to avoid all the dodgy stuff. Okay, because this was previous section, now I just shifted. Okay, but we try to avoid it, but sometimes it's unavoidable, then that's it. For example, in MA, we will need to prove this kind of thing. Why is it true without calculator? Okay, so this is pretty much for a simple comparison test. Next, we will go to limit comparison test. Okay, so you can see that there's a word limit here. So you need to be sensitive. What kind of limit we are trying to see? Okay. So in this case here, we just suppose an greater or equal to 0 and bn greater than 0. Okay, we don't know how to compare a and bn. That's fine. Okay, but one of them is strictly positive. Okay, the other one can take 0 terms sometimes. So what we're going to see here is we can take limit of the quotient an over bn. Okay, if this thing is equal to something else. So from here, you straight away can see that why we require bn to be positive. Okay, because we want to divide it. Okay, divide by it. So what's the possibility of this limit here? So this L can go from say 0 to infinity, right? So if this L is finite, okay, and positive, then what? Then the both series will converge or diverge together. So meaning what? If you know that one of them converge, and then this limit is finite, then they converge together. Okay, if one of them diverge, then they diverge together. Okay. Not that we don't need to consider L to be negative, or do you know why? Huh? We don't need to consider L to be negative. Do you know why? Because the term all we consider are positive, non-negative. Okay, in other words, non-negative. Okay, so the limit won't go negative. At most, you will go is 0. Okay, you will go 0. If you go 0, so there's a condition here. So if you go 0 and the sum of the denominator sequence converges, then an converges. Can you imagine what this ratio is doing or not? Can you imagine? What does it mean by an bn? The limit is equals, let's say, 1. What does this mean? When a is far, an is almost equal to bn. Okay. If the limit is 2, maybe an is almost the 2 times bn. Okay. If its limit is 0, then meaning what? bn grow pretty fast. Okay, bn get pretty large. But if bn get pretty large, bn still converge. the sum of bn still converge, then this statement says that your series of numerator also converge. Make sense or not? Make sense, right? Okay. Okay. So we won't prove this. There's a proof I will upload. That proof is a bit dodgy, so I move it away because some part of that argument need epsilon delta. So if you want to do this proof, you can do it in your project. Okay. So I give you a lot of project idea. Try and think about it. Okay. You don't need to decide first, still quite early stage. Okay. When we go from chapter to chapter, you think that, oh, this chapter I'm more interested. Okay, then go to that chapter and pick suitable topic and do. Okay. Okay, so we're gonna try and use this. So let's try some example. Okay. How about try these two examples first? The other I left as exercise. So let's try this example. 3n minus 2 over n cubed minus 2n squared plus 11. And the other example, ln n over n squared. Let's try these two. Okay, whether they converge or not. So you need to think about what Bn you can compare to. What are the useful Bn you can compare to? Okay, so to save time, so let's quickly discuss. So for the first one, okay, so the first one, what choice can we do? So the choice I made here is an equals, of course, equal to the original sequence here. Okay, so we check that this is greater than 0. Okay, obviously. So I need to find Bn now. Okay, so maybe you can try different Bn. Okay, so let's see why I picked this 3 over n squared here. Let's see if it works or not. So obviously this Bn is greater than 0. Okay, so now we can start and consider the limit between An and Bn. You can keep your choice and then see if it works or not. And then see why mine works. So if I make this choice, what did I get? I will simply get 3n cubed minus 2n squared. Please check the calculation. And then 3n cubed minus 4n squared plus 3. Okay, so what does my n squared does? What my n squared does is just, I write out, I make this numerator power, highest power, and the denominator highest power the same. Okay, this is what I do. That's why I multiply. That's why I consider 3 over n squared. Okay, why is this useful here? Okay, why is this useful? So we now go back to compute the limit of sequence now, correct or not? So to compute this limit of sequence, we can divide by n cubed. Okay, if we divide by n cubed, what do we get? 3 minus 2 over n over 3 minus 6 over n plus 3 over n cubed. In other words, what do we get? 3 over 3, which is 1. So this is in between, a finite number in between 0 and infinity. Okay, so either they diverge together, either they converge together. So do we know about convergence of Bn or not? Bn is what? A multiple of P series. Right? 1 over n squared. Okay, when P is greater than 1. Okay, P equals to 2. So Bn, since
Since the series Bn converges as a scalar multiple of P series, so you can note down why is it true by P series? Because this P is equal to 2, which is greater than 1. Correct or not? Okay. Then by limit comparison test, the original sequence, the series also converges. Okay, converges. Okay, okay. C, if you try C, sorry, not C, second one, ln n over n squared. So just now we tried ln n over n, right? When you try ln n over n squared, it becomes a bit trickier. Okay, a bit trickier. A bit trickier. What trickier? How is it tricky? So you will fail if you try Bn equals to 1 over n squared, Bn equals to 1 over n. Okay, you will fail. These are the obvious choices you make. Okay, so in mathematics, you should try obvious choices. Okay, but if you try these, you will fail. Okay, you should try. You should fail. You should fail first. Okay, learn to fall down, then you know how to walk. You know why? If you never fall down, then once you fall down, you will what? What do you think? And you will die. Hey, some of them will die actually. Some of them will die because that like 怎么说温室里的小花。Okay, it's like you are being taken care too much, and then at the point when you fail, you don't know how to get up. So you have to fail now. Now is the time for failing. Okay, you must fail in my classes. No, sorry. You have to pass. But before the test, you should fail first. Okay, before the test, you should fail first. Only then you can pass your test. Okay, you have to fail. Okay, because when you fail, you will learn new stuff. Okay, and then this new experience only belong to you, personal one. I cannot feel your failure. Only you can feel your own failure. And then this failure will define you. Pretty much. You are defined by your failure. Okay, you are defined by your failure. Okay, so time's up. So I give you a choice. So go back and try. So try Bn equals to 1 over n to the 3 over 2 instead. Okay, try this. Very weird choice. Fractional power. Very weird choice. Okay, go back and try. Okay, try the fail case, try the success case. Okay, you need to feel both. You need to feel the hell and heaven first before you make choices. Okay? Yeah. Okay, so see you on Friday. Okay, see you on Friday.